will continue on what Christian has started to tell you on these quantum spin systems. Before I go to the talk per se, I guess I have to move the things with the, this is of course works that we did on the theoretical side in collaboration with many people, but the main culprit on what I will tell today are Corina Collat, Pierre Bouillot, Shintaro Takayoshi, who was a postdoc in my group and will now have a faculty position in Japan, and two quite recent PhD students, Emmanuel Koira and Noam Kesta. And we had also some theory collaboration with Shunsuke Furuya, who is now back in Japan. And of course, on the experimental side, we were extremely fortunate to work with many experimental groups with several experimental techniques. So the group of the late Claude Berthier in NMR, I guess you know this guy here, since he was the previous speaker, and two other neutron group, André Zeludev in ETH Zurich, and the group of Virginie Simonet and Béatrice Grenier in Grenoble for some of the things I will say later. Okay, so why deal with magnetic insulators? I don't think with this audience I need to remind you why. You already had session on frustrated magnetic system. It's a super interesting problem in itself with a large variety of interesting phases. It covers many materials, many dimensions, many type of interactions. But the point I want to insist on today is the fact that indeed, these are systems. Forget about itinerant system where the interaction will be a screen Coulomb interaction, which is super complicated because it depends on the energy scale and so on. Here we're in a Mott insulating phase. The charge is out of the picture. And at the end of the day, you're characterized by super exchange, which means that the microscopic Hamiltonian actually is relatively easy to characterize and to know, because at the end, it depends only on a few exchange constants that can either be measured or fitted from theory. So we are in a unique situation where, although we are in a condensed matter environment, we can get something which is as precise as, for example, Jean-Philippe told you with the cold atoms, where we know the microscopic Hamiltonian very well, or at the level of accuracy that David was telling you in mesoscopic system, where we can control our microscopic Hamiltonian extremely well. And this allows to do a certain number of things, namely to use these systems as quantum simulators, in which you can really do one-to-one comparison between theoretical calculations and experiments. The second aspect, which was already mentioned several times today and yesterday, is the fact that these systems can be used to model bosons, hardcore bosons on the lattice, either by viewing a singlet and the lowest triplet as no boson or one boson, or even with a spin 1/2, you can say, if I have a spin down, it's the absence of a boson. If I have a spin up, it's the presence of a boson, and transform an Heisenberg model into kinetic energy of bosons hopping on the lattice for the XY term. And then the JZ term is a nearest neighbor boson repulsion, as we heard yesterday. And of course, because you can only get two states, you have a hardcore repulsion between these bosons. The thing which is remarkable is that the magnetic field is acting as a chemical potential for the bosons. So I would say it's the dream of everybody who thought about doing gate doping and whatever. You know, forget about gate doping where you can change, and probably Harold, if he's in the audience, will kill me when he hears me say that, but you can change the density by 10, 20% maybe. Here, you can take the magnetic field and you can do it in 1D, in 2D, in 3D. By sweeping the magnetic field, you can bring the density of bosons from 0 per site to 1 per site. So you can do empty band to full band and totally control your system. So this is a remarkable set of systems where you can view this magnetic system as testing for itinerant bosonic features, but allowing you to dope and control very precisely, so tune very precisely through quantum critical points, and simply measuring the number of bosons in the system by measuring the magnetization of the problem. So this is a quite unique set of features that make this system extremely useful. In addition, you have probes, which are extremely useful to give access to important quantities. As I said, the magnetization gives you the number of bosons. The magnetic field is the chemical potential. And then neutrons, or NMR, give you direct access to important correlation function. The SZ measured in neutrons is the density-density correlation for your bosons. And the S plus, S minus is the single particle Green's function of your boson. So if you can do neutron scattering on this system, you have essentially all the information, or most of the information, that you might want to compute or you might dream to compute for an interacting quantum systems. So this sort of made a paradigm shift on the way one could use spin chains, ladders, spin systems in general, I would say in the 21st century, to coin a date, which is that instead of looking essentially as it was between the 90s and 2000 to quantum spin systems where the magnetic field was not producing much because the exchange constants were typically 1000 Kelvin. So you could not even tickle a magnetic system by a magnetic field of 10 or 20 Tesla, to try to obtain quantum spin systems where you would get small exchange constants of the order of 10, 20 Kelvin, because that way you have the handle of the magnetic field and you can manipulate them extremely efficiently. And that opened really a whole world of experiments that were possible with this system. But there is a price to pay. And the price to pay is that now, because the exchange is very small, of the order of 10 Kelvin, the temperature or the energy at which you're probing this system is not so much smaller than J. Even if you go to experiment at 0.1 Kelvin, it's not like, you know, you have a J of 1000 Kelvin and you're trying to do an experiment at 1 Kelvin. You're safe to use field theory method. But now field theory method is not enough. And we need to get much more powerful solutions to be able to handle these systems, and given the accuracy by which they can give you their microscopic Hamiltonian, make very accurate comparison by the beautiful neutron measurements or other measurements that were mentioned in the talk of Christian. And again, these techniques have known incredible developments in the last 20 years. And this, of course, put pressure on the poor theorists to be able to meet the challenge that is given by the experimentalists. If you want to know more, I had here a reference in which you can find some of the comments and also the references that Christian was mentioning in this talk. So how do we solve? And I will, of course, not go in the technical details, but I just want to mention that we get essentially usually two brands of techniques. The field theory, which is usually asymptotically true. It's good at large distance, large time, temperature small compared to the characteristic energy scale of the problem. And usually this field theory depends on a lot of unknown parameters. So for example, in a 1D system, the Topological liquid parameters which characterize the field theory are not known easily. The amplitudes which relate the microscopic operators with the field theory one are not known. So usually we don't care. We say, oh, we fit a power law, but we don't care about the prefactors. Or we fit a power law and we are happy it's a power law, but we don't know the exponent or something like this. And usually we are happy about this because in condensed matter, very often we are at energy scales much, much lower than the typical energy scale of the problem. Then you have the numerics. And the numerics is, of course, resting on a particular microscopic Hamiltonian, but it's very efficient, but only at short time and short distance. Okay, what is short, what is long, we can discuss, but it's clear that if you want to go to kilometer system, you will not solve them brutally by the numerics. And so very often these two things are essentially disconnected. And the message, the take-home message that I would like to bring is that in the last 15 years in 1D, there was a huge progress that was made on how to practically combine these two methods and try to get the best of both worlds, which is use the numerics where it's powerful directly, and when the numerics would fail, we have the ways to inject in the field theory essentially all the unknown information that we would need to make the field theory essentially an exact theory. And then it can take over on the numerics, and you can do it in real time, in imaginary time, at 0 temperature, at finite temperature, and so on and so forth. And that's what made, I would say, the progress that we could do in this field. And again, we were pushed on one side by the experiments. Now we could push the experiment back and vice versa. And this induced us to make progress. And I will show a couple of the examples. But again, the take-home message, and I think it's particularly appropriate for this conference, is the fact that numerics itself is inefficient, field theory itself is inefficient, or at least not sufficient, and the combination of the two in a very smart way, which actually was pioneered by Duncan Haldane, but to transform it into an efficient procedure took a little bit of time, is what at the end cracked the problem and allowed to really meet experiment and make progress. So let me take a couple of examples. So let me go back to the spin chain and ladders. I will not say anything about the BEC since Christian already mentioned it in great details. And let me go back to the Tomonaga-Luttinger liquid physics, looking at the HP compound that Christian has shown you here already. So this is a system which is a ladder of singlets. Essentially, the exchange here is about 12 Kelvin. The exchange here is about 3 Kelvin. So it's weakly coupled singlets. And the crystal structure of this system is indeed made of very weakly coupled ladders. To give you an idea, the exchange between the ladders is about 50 millikelvin. So there is a wide region of temperature in which you can consider that the ladders are really independent. As Christian was saying, at some point in low temperature, you will have to worry about this. So how do we solve this problem? And sorry, let me go back. So I know the Hamiltonian very well because the exchange constants have been measured by neutrons, so I have no freedom here. So I can take my Giamarchi procedure, my numerical procedure, and say out of this, I will compute the parameters that I need to inject in my field theory. And just to flash curves, it's not important what the numbers are, but just to show you we can do it. You know that in 1D, the physics is described by the Tomonaga-Luttinger liquid, which is the equivalent in 1D of Fermi liquid. And essentially, this theory depends on two parameters, velocity of excitations, which is called U, and a dimensionless parameter K, which controls the decay of all the correlation functions in the system. And taking the Hamiltonian for the ladder, using a Giamarchi procedure, and you heard about Giamarchi in the talk of our chairman on Monday, essentially, we can compute, essentially with arbitrary accuracy, the Tomonaga-Luttinger parameter as a function of the magnetic field, which is imposed on the system. So down to 7 Tesla, the system is entirely in the singlet state. It's like if there is no boson in the system, if you want. And then you start populating the band of bosons, which is why the velocity raises. Then you start saturating the band of bosons, and at 14 Tesla, you have entirely polarized each rung of the system, which is now in a triplet state. And that's why also the velocity goes to 0, because you go to a field. The Luttinger parameter goes on some curve, which is not important, but which we can compute. Then, okay, forget about the green line. It's another it's an approximation scheme that I don't want to discuss. Now we need some correlation functions. So let's take, for example, the NMR relaxation rates, the 1/T1, which is measuring the local spin-spin correlation. And if you take the Tomonaga-Luttinger liquid theory, here is the formula which gives you the T1, the nuclear relaxation time, as a function of the temperature, the velocity, the Luttinger parameter K. This is a d gamma function, and this is the hyperfine coupling. This is the hyperfine coupling, and this is the essentially the amplitude which relates the local operator in the microscopic Hamiltonian with the field theory, which we can also extract from the numerics in ways that I don't want to discuss here. So at the end, now we have a formula in which there is not a single adjustable parameter. Everything has been extracted from the Giamarchi, except the hyperfine coupling constant, which is given to us by our NMR friends, and hopefully exact within 10–20%. Now we can compare, and this is comparison with experiments that were done by Martin Klanczek in the group of Claude Berthier. which I will show you. Again, this is 7 Tesla, this is about 14 Tesla. And here is the measure NMR relaxation time. The red curve is the result of the field theory with the computed Luttinger parameter. There is not a single adjustable parameter in this curve. You could play a little bit with the hyperfine coupling constant, so you can shift a little bit this red curve up and down. So if you want, you can consider this as one number, which is an adjustable parameter. But this curve totally reproduces the experiment. So we have a quantitative fit of the experiment. I wouldn't even call it a fit. We have a quantitative agreement between the experiment and the theory. And it would have been impossible, especially at the time, to extract directly this curve out of a brute force numerical calculation. So by combining the two, we can get the best of both worlds. Since then, this test of the Luttinger liquid theory was pushed further, just to show you if you take the S plus S minus correlation that can be extracted from the neutron, and this was done in the group of Andrei Zeludev on another compound, which is called DIMP, which is a weak rung ladder. So same structure, but this time this is 3 Kelvin, this is about 12 Kelvin. So this is not made of singlets, but this is weakly coupled 1D chain. You can extract this from the experiment, and then at various temperatures, you can make a scaling plot of the structure factor that you have as a function of power of the temperature, as a function of frequency divided by the temperature, and the Tomonaga-Luttinger liquid theory would predict to you that this is a scaling function. And here you have the data, as the dots are the neutron data, and the black line is the prediction of the Tomonaga-Luttinger liquid with one parameter, which is the amplitude, which we don't know in absolute thing, but this is one number. The exponents here are again extracted from the numerics. So I would say for me, this is a spectacular agreement between theoretical prediction and experiments, which I would say validates both. I just want to emphasize that this type of experiment is possible because the neutrons are now able to also reach resolution in energy that were unprecedented before, and otherwise would simply not be able to access this type of regime. You can also do, of course, a direct calculation of the correlations. Here is an example, which is here. This is extracted from the numerics. So the field theory would be good to describe this little part here. And for the rest, the numerics reign supreme. And you can, again, do comparison between experiments that were done in the group of Christian here, and the agreement between the neutrons and the calculation is, again, really excellent. Just to tell you where we are now. Now we can compute the property also at finite temperature. This is a calculation that was done by Noam Kestin, implementing a procedure that was pioneered by Thomas Bartel, I guess when he was still in your group, I don't remember. Now we are able to look as a function of the temperature, how the spectra evolve as a function of temperature. And of course, now make comparison. We have a paper in preparation with Christian on the comparison of this evolution of the spectra. You see a very clear evolution of the minima and the shape of the spectra as a function of temperature. The field theory is still pretty good. Here is a cut of the spectra in the massless phase at Q equal pi. The red line is the field theory. The blue points are the direct numerical calculation. This line here is when the frequency is equal to J, the exchange, above which you don't expect the field theory to work. And you see that there is excellent agreement up to this scale between the field theory and the numerics, showing again that by taking this field theory, but with the parameters coming from the numerics, we can get a theory which is essentially an extremely good description of what you would get at a fraction of the cost of doing the brute force calculation. Now, let me just, in the 5 minutes, I guess, that I have, 7, wow, fantastic. Let me just show you an example of what we can learn, or what is the power of having such exact solution. And for that, I will show you another compound, which is an horrible, it's a compound from hell, it's called BaCOVO. It's an Ising-like spiral, which has very complicated interaction, but its Hamiltonian is relatively simple. It's like an Heisenberg Hamiltonian with Ising anisotropy here. And essentially, so this is a standard Hamiltonian. And this system has an experimental transition when you put the magnetic field perpendicular to the chain, where you see the staggered moment being reduced. And you see, of course, some magnetization, which is increasing in the direction of the magnetic field. And the question was, what is the nature of this transition? And people would say, oh, I get something which is an Ising antiferromagnet. I put a transverse magnetic field. It's the Canting transition. And that's it. That's where you saturate after having canted the field. Easy. Well, you do the calculation with the Giamarchi, and you find that this transition should have been actually 40 Tesla. So 5 times what is observed experimentally. So this is wrong. It's not the explanation. And the explanation we could work out with Shintaro Takayoshi in collaboration with the Grenoble neutron group, which is that actually you have to remember that this compound has a staggered G tensor. So when you apply a uniform field perpendicular to the chain, you also apply a staggered field in the perpendicular direction. And this is this staggered field, which is causing the transition, which is observed. So this was a very nice collaboration between Quentin Fauré, Virginie Simonet, Béatrice Grenier, and our group to start analyzing this transition. Again, I would not go into the details because I don't have the time, but I will be very happy to talk in more detail. This is a beautiful transition because it's a transition which is showing the competition between 2 different topological excitations. Remember BKT, costalis Saules? This is the unbinding of one set of topological excitations. Here you have competition between vortices and the dual of vortices. And this is what this compound is realizing in nature. It's called the double field, double sign-Gordon model. I don't want to bore you with that, but it's a competition between the XXZ anisotropy and the staggered magnetic field. So it's a very nice field theory, which is a double sign-Gordon model. So this is for fun. So this is the field theory, but the field theory would not allow to study quantitatively the transition. It allows you to understand what are the excitations, what is happening in the system. And with the magnetic field, you control the coefficient of this term. And when this term is small, you're dominated by this set of topological excitation. When this term is large, you're dominated by this set of topological excitations. Now, here is the direct calculation from the MRG of the neutron spectra, where you see very well that there is one mode which is going down, but then you have a transition to the perpendicular direction. It's not the same mode which is going up on the other side. And of course, if you do neutrons, you do not detect this because the first step is unpolarized neutron. So you don't see that there is a mode which is different, XX here and ZZ here. What you will see is a mode which is going down and up. So when we did the first analysis and we got back to our colleagues in Grenoble, they said, if it's true, we should see it with polarized neutron. And they did the experiment with polarized neutron, and they confirmed that indeed there is a change of direction of the mode. So this is a very nice exchange, again, between theory and experiments, where having their input on what was going on, we could build some model which was only working because we could get a quantitative description of the system. Here is the same spectra which are calculated, and although we get differences in precise spectral weight, you can see that globally, we get the agreement with what is measured with the neutrons. Okay, we are exploring this compound in much more details. It has beautiful transition when you put the field longitudinal to the chain. It's a Pokrovsky-Talapov transition. So this is really a very nice laboratory. And again, I think we have now the possibility to explore this. So my time is nearly up. So I just want to mention a couple of open problems. Of course, as Christian was saying, we would like to study more complex 1D transitions. I will not say anything about the disorder, but that's of course a fantastic opportunity to have these quantum simulators to deal with the effects of disorder. Out of equilibrium situation, this is where there is a very big challenge on both the theoretical and the experimental side. And as Christian was saying, these are exciting time to tackle these things. And finally, the border, I would say for us now, we have pretty good theories now to describe isolated chains. And so the border is again coupling chains and ladders and trying to describe this type of systems. And that's where we would like to go, where no theorist has gone before. And hopefully we will succeed it. When we want to do this, we usually do RPA, and the RPA works pretty well. Here is, for example, the RPA formula taken from the field theory by the same trick that I was mentioning before. And it fits very well the experiments with one single adjustable parameter. So you would say, wow, RPA is perfect, and that's fantastic. Yes. Transverse coupling. Of course, everything which is longitudinal is done exactly. So the 1D susceptibility, we know, quote exactly, we know from the field theory with the exact Luttinger parameters. So this is the equation which is solved to obtain the TC. But this equation has no reason to be exact because we neglect part of the transverse fluctuations. But nevertheless, it fits very well the experiment at the expense of having a J prime, which we know is not the experimental J prime, and is wrong by, let's say, depending on how you count, 20 or 50% with the experimental J prime. Okay. Here is another example in BaCOVO. If you have other chains, the topological excitation in 1D, which are called spinons, are confined. And here is the computed spectrum resulting from the confinement of spinons. Like if you had an hydrogen atom, you can do spectroscopy of the confinement of spinon. And again, an RPA-like formula. Here is the theoretical scan of this thing compared to the experimentally measured values. And you see the agreement is absolutely beautiful. Yes, but it doesn't work so well in some cases. For example, if you're very close to a quantum critical point, and that's something you can study in this system. We had such a study in collaboration with Andrei Zeludev a couple of, like 2 years ago. And there you can readily see that the RPA formula would give you nonsense. And I don't have time to go into details, but if you compare what you would get for the parameters for the spectra out of the RPA formula, you would not get what is measured experimentally, and you have to find other ways to get this. Okay, so we need to do better, and we have ideas on how to proceed, but this is clearly a theoretical challenge. So my time is up, I stop here. I wanted to show you that we have efficient and precise method for simple 1D systems. And the take-home message is that we can now combine numerics and analytics to get essentially exact methods. We have, of course, a fantastically rich physics for 1D and quasi-1D. We could test Topological liquid theory, and there is a whole exciting new class of topological phase transition that can be seen in this system. And I don't think I need to read the last slide, but I will just leave it, and thank you for your attention.
Much, Thierry. For the benefit of people who are following up via Zoom, we should be relatively close to this screen and repeat again the questions. I think André-Marie was first.
Thank you very much. So at what scale do you match the Giamarchi and the field theory, and how does that scale come in the calculation?
Okay,
the question, so perhaps repeat. Yeah. The question was, at which scale do you match field theory and Giamarchi?
So the field theory depends on 3 parameters: the velocity u, the Luttinger parameter k, and then for each operator, you need to compute an amplitude, which depends on your ultraviolet cutoff. So these things you match from the numerics, and you just need moderately big systems to do this, which are well within access, because you do it with equilibrium correlation function at 0 temperature and so on. Then once you have this, your field theory is entirely determined. Now you could say, at which scale is the field theory correct? In practice, when we compare, it's correct already with 2 or 3 lattice spaces. So it becomes correct extremely rapidly once the exact amplitude, the exact velocity, and the exact k have been put. And you could, well, I'll show you in more detail later, the curve I flash rapidly. you saw this comparison, it's excellent. Now, it depends probably on the operator you're looking at. So I'm sure there might be other operator for which you need to go to much larger length scale.
So the Giamarchi, you would go to what scale to get these parameters?
We do it with typically 100 sites because it doesn't cost much. Because again, we do it in equilibrium. When we plot the direct correlation function, then it's finite temperature, different time. This is a much more complicated calculation. But to get the parameters, I would say now it's essentially an exact calculation with 100 sites without any problem.
Yeah, so to go back just to the very beginning to say that when the statement that we know the Hamiltonians for these systems very well, and I'm not sure that's really true.
So the
question is that it's a comment to say, and it's not just for you, but
so
is the idea that the systems are very precisely described by simple Heisenberg Hamiltonians. I think is not supported in general by first principles.
So let me
repeat the question. The question was how do we really know these Hamiltonians, the microscopic Hamiltonians, so well as we sometimes think or claim?
So first, I agree with you in the sense that, of course, it's interesting, especially if we don't know the Hamiltonian. But what the point I wanted to make is that if you have charge involved, then the caricature, which is the Hubbard model or the UV model or whatever, is really a caricature because you know that all the parameters depends a lot on the energy, the Coulomb interaction will be screened, and it's a complicated process. In these systems, usually, the exchange are essentially energy independent, and I agree with you. In some systems, the Heisenberg model will not be a good expression. Now, on these systems, because we have a possibility to go from the Hamiltonian to the correlation functions without mistake. We can test whether the Hamiltonian is what we think it is or not. If we reproduce the experiment, it is what we think it is. And we can even reconstruct Hamiltonian. Here is a slide that I didn't show, but on this dimpling compound, you don't know what is the Hamiltonian, but you can try an Hamiltonian like this with unknown parameters. And then you run the calculation of the correlation functions, which are shown here, until the point where you fit the neutron spectra. And by the way, the neutron spectra are the dots. The continuum here is the calculation. And once we get an excellent agreement between the two, we know that we didn't miss an essential part of the Hamiltonian. But this is because we can go now from the Hamiltonian to the correlation function with zero mistake, or let's say, a controlled mistake, an epsilon mistake. And yes, if we miss something here, we miss a term in the Hamiltonian. And this is what we saw in BaCOVO. If we don't put the staggered G tensor and the staggered magnetic field, we get nonsense in comparison with the experiment. So your point is well taken, but I think now we have a way to address your concern. We can take an Hamiltonian, do the calculation of the spectra, see if it fits the experiment. If not, go back to the drawing board, and until we determine the microscopic Hamiltonian.
It seems there was a direct comment by Antoine.
Yeah, no, it's not a
No.
comment. It's
Okay.
actually a question. I was intrigued by Aaron's
Because we have,
remarks, and I would like to know a little bit more about what she has in mind, because here my understanding is that we have quite insulating system.
Yes.
So do you mean that ab initio methods yield higher order exchange terms, or can you give us an example?
I mean, okay, so I mean, you can, with first principles calculations, you can actually compute exchange parameters, and often people will, only do as many computations as there are exchange parameters, and not study whether the full spectrum of the model matches what you would predict. I can do ferro and antiferro and get an exchange constant. But what if I do other types of antiferro and require that the model reproduce those energies as well? Not always so easy. And it's just, I mean, the thing is that because you can make this direct connection, it's really interesting to then be able to understand how, to what extent this is telling you about the limitations of the model itself.
So for example, for this type of compound, as Antoine was saying, we have an excellent agreement between the observed spectra and a simple Hamiltonian like this. But we know, if we do ESR, for example, that we have a 3%, order of 3% anisotropies that would need to be also taken into account. But again, if you're not at the level of 3% accuracy, then this is a very good Hamiltonian, and we can confirm it by predicting the spectrum that are observed.
As chairman, let me briefly, I see 3 more questions. Unfortunately, I think we are quite a bit over time. Steve seems to be the most excited one of the 3, so let's have your question. And the others, please discuss it with Thierry.
Yeah, we'll discuss it after the break.
Yeah, sorry about that.
Comments on the comments, so I won't say, just a fast question. Do you think it's possible to include spin lattice coupling in these schemes?
Yes. Yes. The answer is yes.
The coupling, spin lattice coupling, yes. Okay, that was short.
Yeah,
so
well,
I apologize to all the others. We're about 15 minutes over time, and there's no break as far as I can see now. So I hand over to the next chairman. Who is that? Good. So thanks Thierry again.